we've seen that the relationship of being isomorphic is an equivalence relation, and that means that we have equivalence classes of isomorphic vector spaces. And just like we had equivalence classes of matrices by doing row operations, we have equivalence classes of isomorphic vector spaces. So, right, every vector space lives in a whole collection of vector spaces, all of which are isomorphic to it. So, for example, we explicitly produced an isomorphism between P2 and R3 in an earlier video. So those live in the same equivalence class. We also explicitly produced an isomorphism between R4 and the matrix vector space M22. So those live in the same equivalence class. We haven't actually proved that R3 and R4 are not in the same equivalence class, are not isomorphic to each other. It's at the point that we're at, it's harder to prove that two things are not isomorphic than to prove that they are. To prove that two things are isomorphic, you just have to find an isomorphism. But to prove that they aren't isomorphic, you have to prove that it's impossible for there to ever be an isomorphism, which is a much harder thing, right? Proving a negative like that. But one thing that we can do to maybe get a better handle on if there might be sort of unexpected isomorphisms is come up with some nice characterization of when vector spaces are isomorphic to each other, other than just saying there's an isomorphism between them. And one way to do that is to think, is there sort of a nice representative for each isomorphism class? When we were looking at row equivalence, we saw that each row equivalence class has a single reduced row echelon form matrix in it. And so that reduced row echelon form, in some cases, can serve as a representative for the entire class. So we could ask the same question about isomorphism classes. In each isomorphism class, is there some sort of single nice representative of the whole class that we can sort of use as a stand-in for the whole isomorphism class when we're thinking about different isomorphism classes? So what might a nice class be? Well, if we think about the isomorphism classes we've looked at, we've seen that, so like I said, R3 is isomorphic to P2, right? We've seen that R4 is isomorphic to M22. Actually, also it's isomorphic to P3, right? And I mean, we could list other examples. R2, for example, is isomorphic to M12, also isomorphic to M21. I mean, what we're kind of seeing here is that it looks like in each isomorphism class, there's actually only one Euclidean space, right? At least in the examples that I've written down. So maybe it's the Euclidean spaces, the Euclidean vector spaces, that can serve as representatives for each class. But I mean, how could we know if that's really right? I mean, what we need to do is come up with some characterization of what are the other vector spaces in an isomorphism class, along with, say, this Euclidean space or that Euclidean space. Also, we might wonder, well, not only are there any equivalence classes with two Euclidean spaces in them, we have to wonder if there are any are there any isomorphism classes that don't have any Euclidean spaces in them. And in what follows, I have to emphasize that we're only worrying about finite dimensional vector spaces here, right? Things get more complicated if you are working with infinite dimensional spaces. Well, if you look at all of these examples, I mean, not only do the Euclidean spaces appear to be serving as nice class representatives, but it looks like what determines what is in each class is actually, well, it looks like it's the dimension of the vector space, right? If you look at these vector spaces here, everything in this class, at least the ones I've written down, these are all three-dimensional. Right? There are other vector spaces in this class. I can't write them all down because there are infinitely many of them. But at least for the examples I wrote down, you can see they all have the same dimension. It's 3. And here, these all have dimension 4. And these all have dimension 2. So maybe what really characterizes an isomorphism class is the dimension of the vector spaces in that class. So that kind of gives us a good guess. That gives us a target to aim for. So our guess is that 4 finite dimensional vector spaces, two vector spaces are isomorphic if and only if they have the same dimension. So this would completely characterize what it means for two finite dimensional vector spaces to be isomorphic. But this is a guess right now. Of course, having a guess isn't good enough. Really, we should try to prove that this is right, or come up with a counterexample to show that this is not right. But let's be optimistic, and right, if we were pessimistic, we might go looking for a counterexample first. But let's be optimistic and suspect that this is true, in which case we should go looking for a proof first. Because this is an if and only if statement, we have to show two implications. We have to show that if they're isomorphic, then they have the same dimension, and we have to show that if they have the same dimension, then they're isomorphic. So the first one of these is actually pretty straightforward. So let's suppose that we have an isomorphism between two vector spaces. Okay, we have to show that they have the same dimension. So how do you figure out dimension? Well, count up the elements in a basis, right? So let's write a basis for V. So we'll call it beta 1 up through beta n. Let's let this be a basis for V. Okay. Then my claim is, so what I'm going to ask you to believe, or we're going to prove it, but this is what I'm going to prove. My claim is that f of beta 1 and f of beta 2 and so on, all the way up to f of beta n, is a basis for W. If I can prove this, then we're done, because right, if we wrote down this basis for V, this means the dimension of V is n. Well, if I can prove that f of beta 1 through f of beta n is a basis for W, that will mean that the dimension of W is n, because we have a basis with n elements. So if I can prove this claim, then we're done. So let's prove it. I mean, what do we need to prove to show that this really is a basis for W? Well, we have to show that it spans W, and we have to show that it's linearly independent. So let's suppose that we have a linear dependence relationship among the f beta 1 through f beta n. So suppose we have a linear dependence relationship a1 f beta 1 plus dot 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 up through a n f beta n. And this is the zero vector in W. So I'm going to use this subscript to keep track of which vector space this is the zero vector for. All right. Well, on the left-hand side of this equation, right, we know that f is an isomorphism, so it preserves structure. So we can move this f all the way out to here. So on the left-hand side, we have f of a1 beta 1 plus dot 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 plus a n beta n. Okay. And on the right-hand side, we have the zero vector in W. All right. Well, now we have, we can apply the function f inverse to both sides. Remember, f is an isomorphism, so as a function, it is invertible. Right? So apply F inverse to both sides. Now on the left-hand side, F inverse and F, because they're inverse functions, they undo each other, and we just get A1 beta 1 plus dot 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 up through A n beta n. And on the right-hand side, what is F inverse of the zero vector in W? Well, remember, F is an isomorphism. F inverse is an isomorphism. We proved that an inverse of an isomorphism is an isomorphism. And we also know that isomorphisms send the zero vector in one space to the zero vector in another space. So F inverse of the zero vector in W has to be the zero vector in V. Okay, well now we're getting somewhere, because we've turned our linear dependence relationship in W into a linear dependence relationship in V. But remember that beta 1 through beta n are a basis for V. And that means that this has to be the trivial linear dependence relationship. So A1 has to be 0, A2 has to be 0, and so on, all the way up to AN has to be 0. But that means that the linear dependence relationship among the f of beta 1 through f of beta n is the trivial linear dependence relationship. So f of beta 1 through f of beta n is linearly independent. All right, so we have linear independence. Now we just need to show that these vectors f of beta 1 through f of beta n span W. All right, so how do we show that they span? Well, let's take W in capital W. Our goal here is going to be to write little w as a linear combination of f beta 1 through f beta n. All right, so now we can write f inverse applied to little w. F inverse applied to little w, this is something in the vector space V, right? F inverse is an isomorphism that transports us from W to V. So since F inverse of W is in the vector space V, we can write it as a linear combination of the betas, because the betas span V because they're a basis for V. So, so F inverse of W, we can write it as a linear combination A1 beta 1 plus dot 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 up through A n beta n for some choice of coefficients A1 through A n. All right, well then, now let's apply f to both sides. When we apply f to both sides, right, on the left-hand side, we get f of f inverse of w, but that's w. And on the right-hand side, we get f of a1 beta 1 plus dot 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 down to a n beta n. F is an isomorphism, so it preserves structure, and we can write af beta 1 plus dot 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 down to a n f beta n. And I'm missing a 1 right here. So this shows that w is in the span of f beta 1 through f beta n. All right, so now we know, right, we figured out first that f beta 1 through f beta n is linearly independent. Now we know that they span W, and so that means they're a basis for W. So that proves this claim. We have a basis, and that means that both of these vector spaces have dimension n, and so if we have isomorphic spaces, then they have the same dimension. All right, well now let's go the other way. Let's assume that we have two spaces with the same dimension. Let's show they're isomorphic. All right, so let's suppose that dimension of V is equal to dimension W. And let's, just to give this a name, let's call this quantity n. Okay. Now remember here, we are not assuming at first that V and W are isomorphic. That's what we're trying to prove. So what we need to do is come up with an isomorphism. Well, let's let, like we did before, let's let let's choose a basis for v. So we'll call that beta 1 through beta n. So let's let this be a basis for v. And then let's choose a basis for w. We'll call it capital C maybe. And sticking with Greek letters, let's call it gamma 1 through gamma n. Let's let this be a basis for w. And notice that this is where we're using the assumption that these have the same dimension, because we're explicitly writing down the fact that these bases have the same number of vectors in them, because that's what we mean when we say the dimension is n. All right, so now we need to produce an isomorphism. So let's define a function going from f to w as follows. So every vector in V is a linear combination of the basis elements, right? Like this, a1 beta 1 plus dot 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 up through a n beta n. So we can define f by saying f of this linear combination, a1 beta 1 plus dot 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 plus a n beta n, is, we can take those same coefficients, a1 through a n, and multiply them by gammas instead of by betas. So a1 gamma 1 plus dot 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 up through a n gamma n. Okay, now we have so this is a fine formula to write down, but we have a few things that we need to prove. First of all, we need to prove that this is well defined. Right? We need to think about why is it that that writing vectors in V in terms of this linear combination doesn't cause any problems. Well, this is because beta 1 through beta n are a basis. So this representation of any given vector in V as a linear combination is unique, right? For any single vector in V, there's only one way to write it as a linear combination of the betas. That's something we know about bases. And that means that there's no ambiguity in here. There's only, for any given vector in V, there's only one possibility for what these coefficients can be. And so defining this function using these coefficients makes perfect sense. All right, so this is well defined. Next, we need to show that it is onto. Well, it's clearly onto because for a vector w in capital W, we can write w as a linear combination of basis elements in W, right? Our basis elements gamma, so b1 gamma 1 plus dot 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 down to bn gamma n. Then to find a vector in V that f sends to W, well, that's just going to be b1 beta 1 plus dot 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 plus bn beta n. Right? F is going to send this to b1 gamma 1 plus dot 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 plus bn gamma n, and that's W. And so this function is onto. Third thing we need to show is that it's one-to-one. So to show that it's one-to-one, remember we need to show that we need to suppose that f of v1 equals f of v2. Now we need to show that v1 equals v2, right? This is what it means to be one-to-one. So let's write down f of v1. F of v1 is, it's some linear combination of the gammas because f of v1 lives in W. So A1 gamma 1 plus dot 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 plus AN gamma n. But this also expresses f of v2 as a linear combination of these basis elements. And A1 gamma 1 plus dot 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 up to AN gamma n, this is f of A1 beta 1 plus dot 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 plus AN beta n. Okay. All right. Now, but suppose there were another vector that got mapped to all of these things. So suppose this was f of B1 beta 1 plus dot 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 plus Bn beta n. All right. Well, we can write down what each of these is, right? This one is A1 gamma 1 plus dot 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 plus AN gamma n. On the right-hand side, this is B1 gamma 1 plus dot 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 plus Bn gamma n. But now we can move everything to the left-hand side and collect like terms. We get A1 minus B1 gamma 1 plus dot 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 plus AN minus Bn gamma n. And on the right-hand side, we get the 0 vector in W. But we know that the gamma 1 through gamma n are a basis. So in particular, they're linearly independent. And that means that this linear dependence relationship has to be the trivial one. So A1 minus B1 has to equal 0, and so on, down to AN minus Bn has to be equal to 0. And that means that A1 has to be equal to B1, and so on, down to AN has to be equal to Bn. And that means that these two inputs are actually the same. So we've shown that, right, these two vectors, this and this, are actually the same, so that proves that this function is one-to-one. Now there's one thing left to show, right? We've shown that our function is well-defined, it's onto, and it's one-to-one. Last thing just shows that it preserves structure. So f preserves structure. All right. So, right, what we need to do is think about f of, to show that it preserves structure, we can just take a linear combination of two vectors and see what happens. So A1 V1 plus A2 V2. All right, well, you know, V1 we can write to figure out what f does to this, this linear combination. Right? F is really defined in terms of this basis that we wrote down. So we need to write everything in terms of the basis f. So or the basis of betas. So in particular, we need to write V1 in terms of the betas. So let's write it B1 beta 1 plus dot 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 down to B n beta n. And then the same thing for V2. Let's write C1 beta 1 plus dot 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 plus Cn beta n. So you might see where this is going. It's a bit tedious to write this all out, but right, I'm just putting these in and like multiplying everything out and gathering up like terms. So, but you know, I feel professionally obligated to write it all down. So here we go. So f of a1 times v1. So I'm going to distribute this a1 into all of this stuff. I get a1 b1 beta 1 plus dot 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 down to a1 bn beta n plus, and then distribute this a2 to all of that stuff. A2 C1 beta 1 plus dot 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 plus A2 Cn beta n. And now we can gather up like terms according to the beta that appears in each term. So this is A1 B1 plus A2 C1. That should be a 2 right there. All times beta 1 plus dot dot dot. And then let's gather up our beta n terms. There's an A1 Bn plus A2 Cn, all times beta n. And now that we have this written in terms of our basis, now we know what f does to this. F just changes all the betas into gammas. So this is A1B1 plus A2C1 gamma 1 plus dot 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 down to A1BN plus A2CN gamma n. And now we can unwind all of this stuff that we did, multiply everything up and gather everything back up based on the A's. So we have A1 B1 gamma 1 plus dot 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 down to A1 Bn gamma n, right? So that's all the first terms, plus now all the second terms, A2C1 gamma 1 plus dot 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 down to A2CN gamma n. Okay, so right here, gamma 1, oh, this should be an n right here. All right. So now let's factor out this A1. So A1 is A1 times B1 gamma 1 plus dot 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 plus Bn gamma n plus A2, factor out this A2, C1 gamma 1 plus dot 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 plus Cn gamma n. All right, this is A1 times, now look, this right here, this is f of V1, right? This is exactly our formula for V1, except with all of the betas replaced by gammas, and that means that this is f of V1. And then same thing over here, A2 times this right here. This is exactly our formula for V2, but with all the betas replaced by gammas, so this is f of V2. And we finally have that f preserves structure. So, right, thinking back, we now know that f preserves structure. It's 1-to-1, it's onto, it's a well-defined function. So that means that this function we wrote down, f from v to w, is an isomorphism. So let's go back to remind ourselves what we actually just proved. Going all the way to the top, right? Before we knew that if you have isomorphic vector spaces, they have the same dimension. That's probably no big surprise. But what we just proved is the other way. If you have vector spaces with the same dimension, they are isomorphic. And we did this by explicitly writing down an isomorphism. And this is a bit of a surprise. It turns out that for finite dimensional vector spaces, to know what isomorphism class you're in, you only need to know what dimension your vector space has. This is why so many vector spaces look like each other. It's because as long as they have the same dimension, they are isomorphic.